Hello everyone, welcome to the lecture series on kinematic analysis of mechanisms using graphical methods too. In the last lecture we have discussed the velocity analysis of crank and slotted lever mechanism using relative velocity and acceleration analysis method. Now in this lecture we will continue with the acceleration analysis of crank and slotted lever mechanism. So in velocity analysis we have produced this velocity polygon for crank and slotted lever mechanism, and from this velocity polygon we have determined the angular velocity of link OD, which is equals to 2.66 radian per second in clockwise direction. For acceleration diagram, for each of these velocities we will find out the acceleration components. For link CP, we have assumed that P rotates about C. For that we have determined relative tangential velocity of P relative to C, indicated by VPC, which is equals to length of vector CP into the scale factor, which gives 0.989 meter per second. For link PQ, which is a sliding velocity of P relative to Q, its magnitude is equals to length of vector QP in velocity polygon into the scale factor. So length of vector QP into the scale factor gives sliding velocity of P relative to Q, which is equals to 0.74 meter per second. For link OQ, we have determined VQO, whose magnitude is equals to length of vector OQ into the scale factor, which is equals to 0.72 meter per second. For link CP, VPC is equals to 0.989 meter per second, and this is linear tangential velocity when P rotates about C. So VPC will have two components of accelerations, centripetal component and tangential component. Centripetal component of P relative to C is given by V square upon R, that is 0.989 square divided by radius of rotation 0.105. So FCPC is equals to 9.31 meter per second square. For link CP, which is the crank, nothing is mentioned about the angular acceleration of the link, so we safely assume that the crank CP rotates with uniform speed, so its angular acceleration alpha is 0, and so its tangential component of acceleration, that is FTPC, is 0. So for link CP, we have two components of acceleration, centripetal or radial component FCPC is equals to 9.31 and tangential component FTPC equals to 0. For PQ, where P slides relative to Q, we have determined VSPQ, sliding velocity of slider P relative to Q. Since this is a slider, it will not have radial acceleration as well as tangential acceleration. Instead, it will have only sliding acceleration FSPQ, which is unknown. Now this sliding velocity VSPQ of slider P relative to Q is rotating with this link OD, and we have seen in last lecture on Coriolis acceleration that when sliding velocity vector rotates or changes its direction, we have an additional acceleration component called as Coriolis component of acceleration. So for VSPQ changes its direction, that is it rotates with link OD, it will have Coriolis acceleration indicated by FCRPQ. Coriolis acceleration of P relative to Q, whose magnitude is equals to 2 times the sliding velocity of P relative to Q into the angular velocity of link OD, or OQ. So this is equals to 2 into sliding velocity is 0.74. Here it is 0.74, which we have determined from velocity polygon, into 2.66 is the angular velocity of link OQ or OD. So magnitude of FCR PQ is 3.94 meter per second square. So slider PQ will have two components of acceleration: Coriolis acceleration FCR PQ and sliding acceleration FS-PQ. For link OQ, we have determined linear tangential velocity of Q relative to O, which is equals to 0.72. So it will have two components of accelerations since Q rotates about O. Radial component of acceleration, that is FCQO, which is equals to 0.72 square divided by 0.97, that is 1.92 meter per second square. And tangential component of Q relative to O is equals to radius of rotation OQ into the angular acceleration of link OQ, which is unknown. So magnitude of FTQO is unknown. So for link CP, we have two components of acceleration, FCPC and FTPC. For link PQ, we have two components of acceleration, FCRPQ and FSPQ. And for link OQ, we have two components of acceleration, FCQO and FTQO. So in acceleration diagram, we will plot these vectors to find out the unknown accelerations. So this is the required data which we will use to plot the acceleration vectors in acceleration diagram. So comparing the values of centripetal components of acceleration and Coriolis component of acceleration with the paper size, I have decided the scale of 1 centimeter equals to 1 meter per second square. That is scale of 1:1. So first we consider the fixed link OC, for which velocity is 0, so all the accelerations will be 0. So total acceleration of the point C on fixed link relative to the point O on the fixed link will be 0, which will be indicated by zero length vector OC in acceleration diagram. So this point indicates the zero length vector, that is acceleration of point C relative to O. Now next, let us take link CP. For CP, first component to be plotted is FCPC. Radial or centripetal acceleration of P relative to C, which is equals to 9.31 in magnitude. So we'll draw a line or a vector of length 9.31 in acceleration polygon to represent FCPC. Now its direction of FCPC. FCPC is centripetal acceleration of P when it rotates about C. So when P rotates about C, its centripetal or radial acceleration will be directed from P towards the center of rotation C, like this. So this is the direction of FCPC. Centripetal acceleration of P relative to C directed from P towards the center of rotation C along the radius of rotation PC. So we will draw a vector of length 9.31 in this direction in acceleration polygon. Now in acceleration polygon we have point O and C with us, and centripetal component of P relative to C will start at point C or will end at point P. So we have point C in acceleration diagram. So we will start the vector FCPC at point C in the given direction. That is, I will draw a line of 9.31 centimeters in this direction starting at point C. So this is the vector representing FCPC, radial acceleration of P relative to C, whose length is equals to 9.31 centimeters, whose direction is parallel to the radius of rotation PC, and the vector is directed from P towards C in this direction. So direction is the same, and we know that the C is the start point of the vector, which is known in the acceleration polygon. So we have placed the tail of vector at point C. Now to this we have to add its tangential component FTPC, whose magnitude is 0. So FPC, that is total acceleration of P relative to C, which is the vector sum of FCPC and FTPC. Now it is equals to FCPC because FTPC is 0. So FCPC itself represents the total acceleration of P relative to C, which will be represented by vector CP. So the head of vector is point P. Now next, consider link PQ. For PQ, we have two components of acceleration, FSPQ, which is unknown, and FCRPQ, Coriolis acceleration of P relative to Q, which is 3.94 in magnitude. So first of all, we'll plot the non-component of acceleration, FCRPQ. So vector representing FCRPQ will have length of 3.94 centimeters. And now let us find out the direction of FCRPQ. To find out the direction of FCRPQ, what we do? We take the sliding velocity vector PQ from the velocity polygon, rotate this sliding velocity vector, that is VSPQ, in the direction of angular velocity of link OQ through 90 degrees to get the direction of Coriolis acceleration of P relative to Q. So VSPQ, sliding velocity of P relative to Q, the vector VSPQ is rotated through 90 degrees in the direction of rotation of angular velocity of this link OQ through 90 degrees to get FCRPQ. So magnitude of FCRPQ is 3.94 and its direction is perpendicular to VSPQ and the vector will act towards right. Now FCRPQ, this vector will start at Q or end at P. Out of these 2 points, we have point P with us in acceleration polygon. So what we will do now, we will end this vector at point P. That is, we will place FCRPQ such that point P lies at its head, because FCRPQ must end at P. So I will draw a line perpendicular to VSPQ in this direction, and length of that line is equals to 3.94, and the vector will end at point P. So this is FCRPQ placed at point P such that the head of the vector is at point P. And length of this vector is 3.94 centimeters. Direction is perpendicular to VSPQ towards right, and the vector is ending at point P. To this we will add the sliding acceleration of P relative to Q, whose magnitude is unknown, but we know that direction of FSPQ is parallel to the line of stroke of piston P, which is parallel to the length of the link on which the slider P is sliding. So the vector direction of FSPQ is parallel to link OQ, and we know that this vector must pass through point Q and P. Out of these 2 points, we have point P with us, but at P we have placed the FCR. Now we will add FSPQ to FCRPQ. FCRPQ is perpendicular to VSPQ, that is, it is perpendicular to this line of stroke, that is link OQ, and FSPQ is parallel to line OQ, so FSPQ becomes perpendicular to FCRPQ. So we will add FSPQ to FCRPQ at its tail. Magnitude of FSPQ is unknown, so I have drawn the vector of arbitrary length. in the direction parallel to the line of stroke of the piston. The next is link OQ. For OQ, first component is FCQO, whose length is 1.92 centimeters. And we know that FCQO, centripetal acceleration of Q relative to O, that is when Q rotates about O, its centripetal acceleration will be directed from Q towards O, like this. This is the direction of FCQO. Length of this vector is 1.92 centimeters. And we know that FCQO will start at O or end at Q. Out of these 2 points, we have point O in acceleration polygon, which is the start point of this vector. So we'll start this vector FCQO at point O in this direction, like this. So we have plotted FCQO, whose length is equals to 1.92 centimeters. Direction is parallel to link QO, and the vector is directed towards center of rotation O, that is downwards, and the vector is starting at point O. Started at point O. Now to this we will add its tangential component, which is unknown in magnitude, but we know its direction. FTQO is always perpendicular to FCQO because tangential acceleration is always perpendicular to centripetal acceleration. So we'll draw a line perpendicular to FCQO. This line represents FTQO. Length of this line is unknown because we don't know the magnitude of FTQO. So I have drawn a vector of arbitrary length. And I have added this FTQO to FCQO in perpendicular direction. Now read the names of these two vectors. FTQO must pass through point Q, as well as FSPQ must pass through point Q. So point of intersection of both these lines will locate point Q. Now let us draw the vectors. FSPQ is sliding acceleration of P relative to Q. And we have to add FSPQ to FCRPQ. So we have to place these two vectors tail to head. So I have placed head of FSPQ at the tail of FCRPQ. Here is the tail of FCRPQ. So I will have to place the head of FSPQ to the tail of FCRPQ so that both the vectors are added. Now FSPQ plus FCRPQ will give the total acceleration of P relative to Q, indicated by FPQ and represented by vector QP. So this is the acceleration of P relative to Q, FPQ, represented by vector QP. Next, FTQO is to be added to FCQO. So we have to place the vectors tail to head. So FTQO is placed at FCQO so that they get added. So tail of FTQO is placed at the head of FCQO because we want to add these two vectors. And vector addition of both these components FCQO plus FTQO will give FQO, total acceleration of Q relative to O, which will be represented by vector OQ. So this is the resultant acceleration polygon. FQO plus FPQ is equals to FPC. Now next, point D on link OQ, we will use the velocity image principle in the same manner as we have done in velocity polygon. So acceleration image principle, OQD is similar to OQD. So we'll take the ratio to determine the distance of point D from O. Capital OD upon capital OQ, these dimensions are to be taken from configuration diagram, which is equals to small OD from vector polygon, which we don't know. OQ is the length of vector OQ, which is equals to 3.3 centimeters. So OD, that is distance of D from point O in acceleration diagram, is equals to 5.19 centimeters. Now we'll plot the point D in the same sequence. We'll read the sequence in configuration diagram, sorry. So O, Q, D straight. So in acceleration polygon, O, Q, D straight, such that OD is 5.19 centimeters. So here is point D, which is at 5.19 centimeter from O in the same sequence, O, Q, D straight. Now we'll determine angular acceleration of link OD. We'll make use of FTQO to find out alpha QO, that is angular acceleration of link OD. So from this we have alpha QO is equals to FTQO divided by OQ. The value of FTQO is the magnitude of FTQO, which is equals to length of vector XQ into scale factor of acceleration diagram. So we'll measure length of this vector representing FTQO. So length of vector XQ, which represents FTQO, into the scale factor 1 will give the angular acceleration. Length of vector XQ is 2.8 centimeters into scale factor 1 divided by radius of rotation OQ, which is equals to 0.275 meters. This gives alpha QO is equals to 10.18 radian per second square. So angular acceleration of link OD or OQ is 10.18 radian per second square in magnitude. Now to find out the direction of alpha QO, we'll make use of direction of FTQO. So Q relative to O is going in this direction. So FTQO is in this direction. That means acceleration of Q relative to O is clockwise. Thank you.